Hi, everyone. Thank you for attending my talk today. So I am Omar Basha. I'm an assistant professor in the Department of Chemical, Biological, and Bioengineering at North Carolina A&T State University. And today I'll be presenting the work of one of my master's students, Obinna. He should be in the room attending this session, and he will be available afterwards to listen to answer questions. And the title of this talk is Development of a Flow Regime Map for Slurry Bubble Column Reactors Using Power Spectral Density Function Analysis. So let's start off by just talking about slurry bubble column reactors. And this work is within the context of Fischer-Tropsch, so we have the application of Fischer-Tropsch reactors in mind. And for Fischer-Tropsch reactors, there are four main types of catalysts or reactors which have been applied commercially, right? You have your multitubular fixed bed in the top left here, circulating fluidized bed in the bottom left, your microchannel reactor in the bottom right, and the slurry bubble column reactor in the top right, which is really the focus of this work. And a slurry bubble column reactor is a three-phase reactor where I have basically bubbles or gas being introduced into a slurry, which is a mixture of liquid and solid. And this solid is usually the catalyst, and the gas just bubbles through the slurry, and the reactants diffuse from the gas phase to the catalyst surface. Reaction happens, and you get a liquid product, which is taken from this reactor and further processed. Okay, and slurry bubble column reactors have been applied commercially in many applications. The most popular one or the most famous one in these types of presentations for Fischer-Tropsch is this reactor by Sasol in Qatar. And as you can see, the reactor is 10 meters in diameter, 60 meters high. It's a huge type of reactor. And in this sort of context, slurry bubble column reactors give you the advantage of having excellent heat removal, allows you to use very fine catalyst particles, gives you a higher yield per reactor volume. The pressure drop is lower. You also have the option of online catalyst addition and removal, and the construction cost is fairly low, in comparison to a multitubular reactor, where my equipment is a lot more complex, right? However, there are some major challenges, and one of these major challenges is due to the very complex hydrodynamics in this type of reactor, which results in a lot of operational difficulties, a lot of startup difficulties, and a lot of difficulties in troubleshooting and optimizing these types of reactors. So when we take a closer look at the hydrodynamics in slurry bubble column reactors, this has been studied over the years, and we know that there are three main hydrodynamic regimes. Your bubble flow regime, or the homogeneous regime, and this is the most widely investigated regime. It usually occurs at lower gas velocities, and it's characterized by the rising of gas bubbles without much interaction. So all these bubbles are rising, they're all small bubbles, relatively small bubbles rising, not interacting with each other. Coalescence breakup rates are low, and all the bubbles rise at the same time. So constant bubble residence time. So the time it takes every bubble from bottom to the top of the reactor is fixed. It's dominated by the gas velocity, and the reactor diameter does not play an important role at these low gas velocities. And liquid phase, there's no circulation in the liquid phase because these bubbles don't have enough energy to drag the liquid and cause recirculation. And in this flow regime, we see a solid phase concentration profile. So usually the solid concentration is higher near the bottom of the reactor. Okay, and then as you increase your gas velocity, the effect of the reactor's diameter starts increasing. And if you have a small diameter, you get slug flow or plug flow. And if I have a large diameter, I get the churn turbulent regime flow or the heterogeneous flow regime. And slug flow regime, you basically have large bubbles, and these bubbles can be as large as the diameter of the reactor. And in between these large gas bubbles, you have plugs of liquid, and there's the mixing, heat and mass transfer coefficients are very low. You have very severe concentrations in terms of the reactants and the solid phases. And most studies operated or done in small diameter columns operate in this regime, right? Whereas if you have a large diameter column, you get the churn turbulent flow regime. And in this case, we have a lot of recirculation from this rising gas bubbles. We have circulation patterns which cover the entire reactor and different types of circulation patterns, which has been studied extensively. The gas holdup does not increase linearly with the gas velocity. And you see a bubble size distribution, it's classically represented using this two bubble class regime. And in the churn turbulent flow regime, I have enhanced mixing. I have very high heat and mass transfer coefficients. And the solid phase can be easily fluidized. Okay, so we already know the existence of these flow regimes. However, at what points do we transition from one regime to the other, right? And when talking about the transition between regimes, this is not easily delineated. You can't really find these points. And the most commonly used reference is this flow map developed by Decor, which is based on air-water systems, and it's widely used. And if I look at this flow map, I see I have the diameter of the column on the x-axis and the gas velocity on the y-axis. And I basically have some general sort of zones where I have my plug flow regime, where I have my heterogeneous regime churn turbulent, and I have the homogeneous regime here at the bottom. Okay, these flow maps are usually based on visual observations. So when you're looking visually to try to get these trends or try to understand this behavior, you're limited to near the reactor wall. You can't really see towards the inside of the reactor. And then as the solid concentration increases, your visibility drops significantly, so you really don't see anything. So really, we need another approach. We need to find another way besides this visual approach, looking through reactor windows to try and delineate or find the demarcations between the regimes. So the other approach proposed in this work is to have a look at the pressure fluctuations. And pressure fluctuations, this approach has been previously implemented. Previous co-workers looked at pressure fluctuations, others looked at, gamma fluctuations of other signals. And usually the frequency of fluctuations will indicate a change in hydrodynamic regime. So at certain regimes, we have different frequencies of the fluctuations, and as the regime transitions, we see this changes. And pressure fluctuation will depend on the gas velocity, the pressure, and the catalyst concentrations, right? So we already know this. So therefore, the objective of this work is to analyze over 400 experimental pressure fluctuation data sets to try and get an understanding of the boundaries within the churn turbulent flow regime, okay? So we have 400 experimental pressure fluctuation data sets, all conducted within the churn turbulent flow regime, and we want to try to understand the boundaries of this regime. Okay, so let's have a look at the experimental data, or present the experimental data basically, which was used in this analysis. The experimental data we used was provided by Dr. Morse's group at the University of Pittsburgh. Their data was measured in a pilot scale slurry bubble column reactor they have over there, which is 15 centimeters in internal diameter and 3 meters high. And the experiments cover a wide range of operating conditions. Most of them resemble the Fischer-Tropsch operating range, so temperatures between 320 to 500 Kelvin, pressure from 4 to 31 bar, your solid concentrations from 5 to 15 volume percent, and your superficial gas velocity between 0.05 to 0.3 meters per second. And we have experimental data for different gas, liquid, solid systems. So there's a wide range of experimental data which we think could help us provide a reasonable analysis of the pressure fluctuation. Okay, and usually these experimental data, or usually these experiments are done using two main methods. The first method is called the manometric method, where I basically just measure the pressure drop between 2 points of the reactor. And the second method is called the dynamic gas disengagement, where I let the reactor reach steady state and then suddenly I stop the gas flow and I monitor this pressure drop or the decrease in pressure along the reactor with time. And it's basically the time it takes for all these bubbles to disengage. And I can sort of make some extrapolations about the nature of the bubbles from this data. Okay, so this is the experimental procedure, and from this experiments I get, I have the pressure fluctuation data. Okay, this pressure fluctuation data is not directly used, but it's being measured with every experimental run. And if we have a look at the different pressure fluctuation plots, you can see that, you know, maybe we can visually try to get some trends. However, it's not easy at all to get any specific information. And we really need a better approach to translate this pressure fluctuation data. Okay, and this is where the power spectrum density function analysis comes into the game. So let's, before talking about the PSDF or power spectrum density functions, let's talk quickly about signals. So signals fall into, or signals can be classified into either periodic or non-periodic. So periodic signal basically repeats itself over a fixed length of time. And it can also be classified as deterministic and random. Okay, so deterministic signal can be mathematically characterized completely in a time domain, whereas a random signal can only be described in terms of probabilistic parameters. All right. And frequency domain representation. So in case we have arbitrary wave shapes, so this is the case with the pressure fluctuations you saw earlier, they're somewhat arbitrary. We know that these are random signals, right? And we really can't use a Fourier analysis to get an answer analytically. So therefore, we need to use a power spectrum or a power spectrum density concept to try and analyze these signals, okay? So it's just sort of the general idea. A lot more information can be found elsewhere, of course. And the power spectrum describes the distribution of power versus the frequency. And you basically calculate the average signal power, and this is the equation for it. And it shows the strength of the variations in energy as a function of frequency. It shows the frequencies at which the variations are strong and the frequencies at which the variations are weak. And it has a unit of energy per frequency. And it's based on the Fourier transformation of a discrete signal to a complex expression. And you can find the mathematical details elsewhere. But what we did is we basically implemented the PSDF this transformation into MATLAB. So we translated the random pressure fluctuation signals, and we got the PSDF plots. And we had an automated MATLAB algorithm to do so. Okay, so once we did that, we had 376 feasible PSDF plots, and this is what a PSDF plot looks like. You know, you can see like basically the power frequencies versus you see the frequencies and their probability, right? Okay, so we already know a few things based on previous work and based on, and we already confirmed these facts that at low frequencies or lower frequencies correspond to larger bubbles. A wider frequency distribution is usually observed for lower catalyst concentration, whereas higher catalyst concentrations shift the frequencies towards the left or towards lower values, and higher pressures increase the PSDF plots of higher frequency signals. So high pressures tend to shift the plot to the right. Okay, so we already know this, and we verified this from our plots. So it sort of matches what little has been done before. So it gave us some confidence. And then next step, we did a visual analysis of these PSDF plots. And upon visual analysis, we grouped them into three main groups based on their frequency strength. So group A had frequencies from 10 to the 3 to 10 to the 4. And we said that this group corresponds to the growing bubble regime, where I have a majority of small bubbles. Group B is between 100 to 1,000 hertz. And this is the bubble transition regime. And group C is between 10 to 100 hertz. And this corresponds to the stable bubble regime. So we sort of used a very basic metric to divide our plots into three groups visually, just by having a look at, you know, where do I have the highest frequencies? If I have the highest frequencies in this end, then this set of parameters is in the growing bubble regime. Frequencies in this end, this corresponds to the bubble transition, and frequencies higher in this end, then this is the stable bubble regime. And then once we grouped them, we looked at the experimental conditions corresponding to each group. And we're working on delineating the following operating conditions to characterize each of these groups. Basically, we want to know about volumetric mass transfer coefficient, bubble velocity or gas velocity, interfacial area, pressure, temperature, and gas hold. Okay. And these are just some generalized results for the superficial gas velocity, pressure, and temperature of each group. And as you can see, group A is towards the lower superficial gas velocity. The pressure, this is the pressure range, and this is the temperature range, similarly for group B and group C. So we have some information where we're about which operating conditions correspond to which group and which operating conditions correspond to which regime, sort of the growing bubble regime, the transition, or the stable bubble regime. And at the moment, ongoing work aims at linking all of these above parameters to some physical properties of the system. So at the moment, we're doing an analysis to try and look at other parameters, primarily the liquid density, viscosity, surface tension, the gas density and nature, and the solid density. And hopefully we can try to also get an understanding on the effect of the physical properties of the system on basically the limits of the churn turbulent flow regime. And finally, we're still looking at the best way to present a flow regime map for the churn turbulent regime. And what's the best way to present it? What's the best parameter to put on the x-axis and the y-axis? And Obinna, my student who did this work, he should be in the room, and he will be there to answer any of your questions. This is it from me today. Thank you very much for listening. If you have any questions later on, please feel free to send me an email, and I'll get back to you as soon as possible. Thank you very much.